Log on, tune in, find out. Another good idea from Cambridge.
New session with our last speaker this morning, and it's Professor Vazi, and he's talking on new non-elliptic methods in the analysis of the Laplacian or conformally mapped asymptotically
title. So I would like to start by thanking all the organizers of this wonderful program and apologize to all the participants for the awkward time. So originally the schedule had to be rearranged, so close to the time for the departing when it was originally scheduled to do. So I tried to not run over time though, so you can get your lunch early enough. So fortunately, this conference has in the title Analysis and Geometry in addition to inverse problems. So I won't get to inverse problems. I will talk about both. I won't talk about inverse problems. I do talk about analysis and geometry. Now, however, I do hope that so there are certainly people working on inverse problems in related areas, for example, Stefanov and Ullmann on hyperbolic spaces. I mean, certainly in exact hyperbolic spaces there has been a lot done, but certainly asymptotically hyperbolic spaces. So there's certainly some interest in these problems. And in addition, even in problems where there's no asymptotically hyperbolic structure, so maybe you have a finite boundary, not even an obvious boundary, sometimes sort of suitable rescaling of the problem gives rise to similar phenomena. So this is the subject of a current project with Gunther Ullmann, about which I would have liked to talk, but it would have required about another month to get a bit farther and be sort of more sure of everything. So I can't talk about that, but I can talk about some of this background. So I would like to start by describing asymptotically hyperbolic metrics. Maybe the right place to start is to say something about hyperbolic space itself. So there are many ways of understanding this, but perhaps the easiest way is to think about Minkowski space in one higher dimension, so n-dimensional. So consider Minkowski space of one higher dimension. So this is just Rn plus 1 with a metric whose sign you get to decide. And so I'm going to choose lots of minus signs. So the zn's are the coordinates. Zj's are the coordinates. And so then what you do is you consider the upper half of the two-sheeted hyperboloid. So let me try to draw a picture. So it's supposed to be a three-dimensional picture. So this is Zn plus 1. So n is, I suppose, 2. And so you consider the upper half of the two-sheeted hyperboloid. So there's a bottom half to it as well. And so this would be the quadratic Zn plus 1 squared is Z1 squared. So Zn squared plus 1. So, and Zn plus 1 is positive. And then what you do is, so this is the metric on the ambient space, the Minkowski space, and then just pull back the metric to this submanifold, and you get the hyperbolic metric. So pull back. So let's call this, I don't know, X. Pull back Minkowski metric. X. So now you have an n-dimensional Riemannian manifold. So I should say that this is a Lorentzian metric. So when you pull back a Lorentzian metric to a codimension one submanifold, various things could happen. You could end up with the Riemannian metric as you do here, or you could end up with a Lorentzian metric, or you could have some degeneracy. So in fact, it's useful to have another So this is hyperbolic space. It's useful to have another example, which is the one-sheeted hyperboloid. So the Sitter space in n dimensions is just the one-sheeted hyperboloid in Minkowski space with the pulled-back metric. And this is Lorentzian. So this will come up at some point. Hyperboloid. Okay, so you just have to change the sign there. Okay, so we have a concrete, very concrete description of hyperbolic space. Now, often it's convenient to think of hyperbolic space as a compact space with sort of an ideal boundary at infinity. And so the typical model that is good to think about is the Poincaré model. So there you identify hyperbolic space with a ball, maybe the interior. Let's think of this like the interior of the closed ball. And so roughly speaking, what you're doing here, so because hyperbolic space there is a graph, so you can think of R, it's just a graph over Rn. So effectively, you just have to compactify Rn into a ball, which is rather easy to do. You don't have to do anything in the angular variables. That's a sphere. It's already compact. You just have to compactify the radial variable, which you can easily do. And so the net result is if you work out what happens, so here's now the ball picture. And then I'm going to have a boundary defining function x, and then there's some variables y in the boundary, so maybe I should call them omega. So the angular variables. And here the x could be given explicitly in terms of the radial variable in Euclidean, the Euclidean R, so something like x is 1 over r, I think, actually. So actually, you can take x equals 1 over r, where you write z1, zn as r omega, and just compute. I mean, it's a straightforward computation. So what you end up with is the metric has the following form. So completely explicitly, actually, I think. Well, you get a negative sign here because I put in all those negative signs. So Mihalis, the friends will probably say it's all my fault, which is true. So you end up with a metric like this. So it's really a negative of a Riemannian metric. Okay, so this is actually I think exact as I wrote down. But so the point is that so asymptotically, which is what we care about, as x goes to 0, it has the following form. So maybe I'm going to generalize this cross-section sphere to something else. So I'm going to work on some random manifolded boundary, and it will look like dx squared plus some metric h, maybe depending on x, y, dy. You could also allow cross terms, although there are some theorems that you can eliminate those anyway, so it doesn't make any difference. So some metric like this, where, well, so after taking a minus sign, the negative. So it has this form where h is, where this thing is now a Riemannian metric on the boundary. So in this case, a sphere, or more general boundary. So again, this, of course, is a sort of a long history. And so this, so really, we're going to think about this general class of metrics. And so for this general class of metrics, so if x is now, say, just a, well, let me write x bar, but I might forget the bars at some point. This is a compact manifold with boundary. And you take x, little x, to be a boundary defining function. So this just says that equal to 0 on the boundary, a positive inside, and non-degenerate. So the differential is non-zero on the boundary. So non-degeneracy defines the boundary. So then you can think about matrix of the form, basically G equals, maybe I want to call it, I don't know, G tilde over x squared, where G tilde is a smooth metric up to the boundary. So that's exactly the setting we had. So this is our metric G, and it has the form G tilde over x squared. So it fits into this framework. And so again, in the actual case of hyperbolic space, there have been a lot of or quotients of this. There's been a lot of work on some various aspects of this. I mean, in particular, what's most relevant in here is Peter Perry worked quite a bit on quotients of hyperbolic space, or scattering theory for these sort of things. Of course, in something that's not quite directly related to this, but I mean, it's not exactly this, but there's a connection, is cusps, for which there's been a lot of work, like Fadeev and Lex Phillips and others. But I'm not going to mention that, talk about that. But in this sort of framework, it was a theorem of Mazzeo and Marrow's that the resolvent of the Laplacian has an analytic continuation. So let me just write down the Laplacian. So it's just the Laplace-Beltrami operator that Slava Krylev talked about quite a bit quite extremely efficiently last week. Operator. And so roughly speaking, so modulo low-order terms, which are not to say that they are negligible, this roughly looks like, with such a metric, and that roughly looks like the following: x dx squared. Maybe I should add just one lower order term, since it's of some relevance, except that, okay, so my general convention is, as in Fourier analysis, this d stands for 1 over I times the standard differentiation. And so you end up with some i's if you write things this way. So I think this is right, but I'm not going to guarantee it. So this is the Laplacian on the boundary, so plus low order terms. I mean, things that vanish, or higher order terms, maybe I should say. Things that vanish to higher order as x goes to 0. So x goes to 0 is the boundary. Okay, so you have this is the Laplacian. And then this is a self-adjoint operator on L2, and so you can consider its resolvent, which, I mean, analogously to very sort of setting like cusps, you might want to renormalize so that what you're really looking at is you're subtracting away the bottom of the continuous spectrum. So maybe I should say that the way the spectrum of this looks like, so here's 0. So the bottom of the spectrum is, if I got my numbers right, so it's n minus 1 squared over 4. So it's a continuous spectrum here with possibly, I think we have some eigenvalues below. And so corresponding, it's natural to normalize it like this. And so you get to make a choice. So so say this is when m sigma is positive. So that's sort of the physical half plane now. So because of using sigma squared, you're essentially opening up the spectrum. So this is what let me write spec, so it doesn't look like a sigma. This is the sigma plane. So what was this continuous spectrum here is now the real line. And if I manage to be consistent, there might be some eigenvalues here. And then the question you can ask is, do you get an analytic continuation across the spectrum? And then in this generality, again, so there are lots of other theorems in various cases, but in this generality, it's a theorem of Mazzeo-Marrow's. And maybe I should just add Perry as well. So special case Perry. Is that the resolvent actually continues meromorphically. So there will be some provisos in a moment, to all of C. Now, okay, so I believe it was noticed by Borthwick and Perry that there were some small issues in this Mazzomero's argument, so there's some incompleteness in it. And in fact, things can go a bit worse, or maybe you could say quite a bit. And this was really properly figured out by Guillermo, who showed that in general, so hence the provisos, there are some essential singularities at some pure imaginary, essentially integer, or maybe exactly integer, points. So when you for the analytic continuation, however, these do not appear if G is even in X. So I mean, you can make a much nicer definition, but this means that description of this, i.e., if you already put the metric in that form, which is convenient for the statement, if H has only even powers of X in its Taylor series, so only the Taylor series matters. And if you want to go in some finite distance, then only finitely many terms matter. All right, so that's a very good picture. Now, what I would like to explain is a sort of different way of thinking about this theorem, and so proving this, and doing one other thing that's been somewhat puzzling to people who are interested in scattering theory in these sort of spaces, which is that a natural thing you would like to do is to I mean, in addition to say that this resolvent has an analytic continuation, typically you would like to use this resolvent in some integral formula, say. So you actually want to integrate it on maybe a contour or something similar. It's going out to infinity. So in fact, you really want some uniform estimates as sigma goes to infinity, at the very least in strips. So strips. The imaginary part of sigma is finite, and so the theorem then is that so one part is that so there's a different proof of the result of Guillermo plus in the even setting, so plus the following. so assuming that H is even in the sense of Guillermo, assume H is even, so then one has let's put it this way, non-trapping high energy non-trapping high energy estimates for R sigma in strips. Now I should say here is that in a special case, by a different method, so a parametrics construction, special case when G is actually asymptotic to exact hyperbolic metric, as opposed to in this generalized sense. So like second order agreement, something like that. This was shown in joint work with Maros and Sabareto. recently. Again, so that's a much more involved argument in a special case. But of course, it's a parametric construction, so you get more than just what I'm claiming here. So to put this in the context, you indicate a bit where things going to go. Let's see. So since you're talking about even matrix, a natural thing to do is you change the smooth structure, well, in a maybe drastic but really rather simple way. Well, simple way. So let's declare x squared as the new boundary defining function. So of course, if you write an actual product decomposition, this makes sense, but I'm near the boundary, but really it makes sense, period. And so it's an even version of x, and so basically even functions, so even in Taylor series in x, that is, even functions on x become smooth functions on x even. So given that the hypothesis is an evenness on the metric, this seems like a reasonable thing to do. And so now you have a perfectly nice manifold with boundary, this x even. So I usually had bars, but it's really x bar. Drop bars from now on. So x itself is compact, has a boundary. Okay, and so now you just have a nice manifold boundary, and then you just have the standard Sobolev spaces on this, and you, for the high energy estimates, you also care about Sobolev spaces, and in fact semi-classical Sobolev spaces. So these show subspaces on x even. So, for example, I mean, the sort of things that you might want is that if s is an integer, positive integer, you could take something like, I mean, locally anyway, you could just take something like hd. So h is your semi-classical parameter. This is a Planck's constant, so but a semi-classical parameter. So this is just L2. So this would be the so locally anyway. And then it's a partition of unity. So this would be the HS sub h norm of u. Maybe I should say x even. So the h is, so this is the small parameter. And as h goes to 0, you have sort of less and less weight on the derivative. So this sort of thing showed up in Colin Guillermo's talk for Kalem estimates, which are sort of different, but I mean it's not unrelated. The way these h's show up, of course. Okay, so with this, so the translation is, of course, the translation we have this sigma. Is that sigma inverse plays the role of h. And so then the high energy estimate so this non-trapping estimate that I stated, so it's going to look as follows. So non-trapping is because this is what a non-trapping estimate would look like, for example, in Euclidean space. If you perturb the metric or add the potential, which is non-trapping, and then you care about what happens to the resolvent as the spectral parameter, or for the semi-classical, I mean for the perturb problem, goes to semi-classical originally goes to 0 for the particular problem. So here's the estimate. So if, okay, so I didn't say that. So high energy estimate. So this is if X is non-trapping. So this is an estimate. This is, so if geodesic flow on X is non-trapping. So this is say that all geodesics. So remember, there's this 1 over x squared factor in the matrix. So the boundary is infinitely far. So it takes infinitely long time to get there. But all geodesics eventually leave. Let's put it this way. These fixed compact subsets of the interior. So I dubbed the bar. So so if X is non-trapping, then you have the following kind of estimate. So I'm going to, oh, I should have explained one more thing here. And actually, so I'm going to get into trouble at some point with my normalizations. So this is the semi-classical space. This is less than some constant times sigma inverse. So the norm here is hs minus 1 sigma inverse. So in strips. Less than c, where the c has actually is not arbitrary. This is for s bigger than half plus c. I mean, I forget now which way. I had my normalization that imaginary part is positive. To start, if sigma is positive, is the physical half plane. So the question is really what happens when this is negative. And so what this is saying is that you will get a uniform estimate in strips. So this is the non-trapping estimate. So if you had sort of ellipticity, you shouldn't be losing anything. So you should get a sigma to the minus 2 because of how things get renormalized. But the non-elliptic, so this is sort of the analog of a hyperbolic estimate. And so there's a loss of a sigma. So if X is non-trapping, then you have an estimate like this. But it's not quite in any space, which is what would be the, say, in the Euclidean scattering. There's a minimum amount of regularity you have to impose. You'll notice also there's a loss of one derivative. That's again sort of the hyperbolic phenomenon. And the minimum amount of regularity you have to impose gets larger and larger the farther you want to continue into the complex domain. Okay, so you can say various extra things about this, but probably that's not what I should do right now, but rather explain where this. How can you rethink the problem that's originally posed and put it into a different framework? So I should say originally. So of course, if you're in actual hyperbolic space, you can use the explicit hyperbolic resolvent to do various things. The Mazzucaro's picture was to construct an approximation, so parametrics for the resolvent using what they call the zero double space. So it's sort of analogous to how you construct inverses for elliptic pseudo-differential operators on, say, domains without boundary, but much more involved. There's some blow-ups and such things. So I want to do it in explain in a different way, which involves extension of the problem across the boundary. Now, so let's do that. So this idea of extending across the boundary is not a very good idea before you change the defining function from x to x squared. So notice that extending, so once x squared is your defining function, what does it mean that you go across the boundary? So x squared is positive on your side of the boundary. You want to get across. So that means that x squared becomes negative. So formally, this means, in a very formal sense, is that x gets multiplied by an I, or minus I. So what this is, in a very formal way, analogous to, but is sort of quite different how things really work, is a rotation into the imaginary domain. So this is what physicists might call a Wick rotation in the boundary defining function when you go across the boundary. So okay, so let's see, how about you raise the just find my operator. Okay, so concretely, so the following happens. So we analyze, and you really shouldn't think of it as that G because of what I'm going to say. You really should think of it as the whole spectral family. So minus sigma squared by sort of conjugating this by appropriate things, by transforming this in such a way that one can extend it across. So let's give so mu equals 0, where mu is x squared. So effectively this means, so x is, this is very much in quotes, x in some sense gets replaced by ix. Now, so it's of course quite crazy to put it that way. So very concretely, you can write down something like p sigma is the following thing. So to start with a mu positive, and then you just check that this has what the desired properties. So this is, and then the minus is just if you, depending on what you want to end up with, thanks given the normalizations of the various things. So again, you can just write this down. So it looks crazy like this. Oh gosh, so I think it's a plus. So if you start with, so e.g., G is just it's just hyperbolic space, and you do a similar thing in general. But let me just write this down as an illustration. So, oh gosh, there's an extra thing. So this is not a completely explicit formula if I write it this way. Except that I'm sure I get my ends right. So this is plus 1, this is minus 1, I think. So I just wrote down an operator of this form. So what we are doing is this is a conjugation. This mu power is just a conjugation of this hyperbolic Laplacian, well, modified by the spectral parameter, and this is a potential that's ignorable. But this is when I would get an explicit formula that I want to write, might want to write down. So you conjugate this, and then you multiply it by a singular factor. So conjugate and multiply by a singular factor. Now, if you singular factor, but the effect of all this, so doing this the right way, the effect is it continues. To mu negative. So it sounds like a bit mysterious if I write it like this. It's not at all mysterious. So I write it down in where it comes from in a much more natural way. But I'm trying to I should try to find the formula for this. So here's the explicit formula for p sigma. So this is going to be with the notation that mu is 1 minus r squared. And so the way you can think about this is in this Poincare model, r is really the distance from the origin. So mu is really the boundary defining function. R equals 1 is where mu is equal to 0. So what p sigma is in this picture is something like minus 4 r squared mu d mu squared plus, it's all explicit. So there's nothing, mysterious going on here. Maybe some lower order terms. So I don't want to think about this necessarily as a lower order term because semi-classically it's not. in the high energy sense, it's not. So the thing to notice about this kind of an operator, this is elliptic. So if you compare these two terms, this is elliptic. So continuing across the boundary is, of course, no big deal. I mean, the original operator I wrote down, which might be gone, had some smooth coefficients which are degenerate. So of course it continues across the boundary, but you want it to do it so in a non-degenerate way. So this is elliptic. If you compare these things, elliptic if mu is positive, signs match, but it's hyperbolic. This with mu playing the role of time. If mu negative. And so if you want, you can just write down the principal symbol for this. So ignoring the sigma just in standard sense, the principal symbol of P sigma is, so you might care about the in a high energy sense as well, so then you have to do more. It's just, I think the way I wrote it, minus 4r squared mu psi squared minus r minus 2 eta squared omega, where psi is the dual variable to mu. So there are no boundaries now. We just went, mu equals 0 is just some hypersurface in this bigger space. So psi is dual to mu equals 0, eta, I mean to mu, and eta is dual to omega, or y, whatever for the boundary variables. So that's our principal symbol. And again, you can of course see similar. That's elliptic if mu positive, hyperbolic if mu negative. So what you care about if you have a non-elliptic problem. So I'm going to try to draw. What I should draw is the cotangent bundle of. Okay, maybe I should extend x even extend. So I'm just adding the phase variables as well. So that's these. But let's just quotient out by the r plus section. So I'm just looking at, I mean, this is the usual thing in macro analysis, just look at the high frequency behavior. So that's the easiest thing to draw. All right, so here's going to be my picture. This is my mu variable. So mu equals 0 is the boundary, or what used to be the boundary. So this is what came from hyperbolic space. And this is the continuation. Now the operator is elliptic inside, so there's nothing too much going on. But in the outside, it's not. And so what happens is that you have a characteristic set. So this is p equals 0. And what happens is that these points, which geometrically would be the conormal bundle of mu equals 0, these are so-called radial points. So these are the things that show up in scattering theory. So these are radial points in the sense of Hermander. So the Hamilton vector field is a multiple of the generative dilations of this dilation action here. This shows up in scattering theory, say Euclidean or n-body, or even just Euclidean. Scattering theory, for example, in the work of Siegel and Suffer, this would be called the correspond to the propagation set. All right, and so then. What happens is that, so the radial point, so that is to say, the flow, these are critical points for the flow. So you get, once you go to this quotient, you end up with the Hamilton vector field on this space. So that's a classical flow. Will give rise to a vector field on this space. And these are critical points for the flow. So it takes infinitely long time to get there. And then the way, however, so these can be analyzed perfectly well. I mean, scattering theory has been doing this in other settings, and so these can be analyzed. So there's some other issues that I'm ignoring, but analyzable by sort of scattering theory tools. So, for example, Hiroshi Sozaki worked on some related things, and so Marrow's general framework is where this would nicely fit in. And so what you can do is you can get estimates. So again, this is related to what Guillermo talked about yesterday. You get estimates both for P and its adjoint. And so this gives you almost existence and uniqueness modulo fine dimensional obstacle. Now, maybe in the last 2 minutes, just say something about, so it was very sketchy here, and this looks like a crazy thing to write down. So where this really comes from, so I mentioned the Sitter space in the beginning. That's a good way, Minkowski space is another good way to think of where this comes from. So I wrote down in this particular case what you do, and the similar thing works in general. But here's the de Sitter space picture. So I said the Sitter space was this one-shaded hyperboloid. So again, you might as well think of it as a finite cylinder. So it's in fact conformal. It's conformal just to a finite cylinder. Now, of course, a conformal change in the metric changes geodesics drastically. However, it only reparameterizes null geodesics. So this is a Lorentzian space, so the null geodesics. And so what the so the light cone for the Sitter space, so this is maybe x, and then you have some variables, I know y, maybe we should call it rho or something. So roughly speaking, the matrix looks like d rho squared minus, I don't know, dy squared over rho squared. But this is ignorable as far as null geodesics are concerned, so the backward light cone just looks like this. So now you can do the following from a fixed point. So pick P, maybe Q. Pick Q on the future infinity boundary. So again, you can do this from a Minkowski picture as well. So pick Q on future infinity and introduce polar coordinates there. So to distinguish the light cone. So, or in other words, blow it up. Or maybe spherical coordinates, I should say. Okay, so you get a picture like this. This is the light cone. And so what happens is that if you take the, here you have a D'Alembertian. Take this D'Alembertian, take a Mellin transform of it along these fibers. You get an induced a family of operators here. And what that family turns out to be is exactly this family P sigma, the way I wrote it down. And if you now go the opposite way, you will see that in here you get, as an induced operator, the spectral family for the hyperbolic Laplacian. So maybe just a philosophical statement, and then I stop. So one way to think about what's happening here is that maybe it's not a very good way to think about the spectral problem for the hyperbolic Laplacian or estimated hyperbolic Laplacian as a differential geometry problem. It's better to think about it as a problem corresponding to symplectic geometry, something happening in the phase space. So what these sort of things do is they rearrange phase space, and this rearranged phase space, and once you did this rearranging, so you don't just regard this as a sigma as an extra parameter, I mean as a constant, it sort of plays an active role, is that you can continue across the boundary and then use, so I have to do something here that I completely did not discuss at all. But you can put this now on a manifold without boundary and just use standard techniques on manifolds without boundaries. So thank you for your attention. Sorry for going slightly.
Okay, it must be better finish here because
lunch
lunch is
time.
20 minutes.